Another statistical feature that we need to learn is the data distribution. And basically, the shape of the spread of the data around the mean is called the distribution. Basically, it's just the distribution of the data. And it is represented by histograms, which are the plot of the data points sorted based on their frequency in the intervals. So we will get some intervals or bins, and in each interval, basically we divide the data to intervals, let's say, and we decide how many data we have in each interval, and the number of data gives us the frequency. And according to frequency, and the frequency will be in the y-axis, and data points or the interval means will be in the x-axis, and we will plot the intervals with the amount of frequency, which gives us the histogram. Let's have an example about this. So this is our data from the previous example. You can see this, and we calculated also these, and we basically have some interval lower and upper bounds in here. So intervals will be in equivalent length. You can see here from 636 to 640. Actually, the minimum is 633.95, but we took it as 636 to 640. Then from 640 to 644. You can see that in between these, there's only this data, and in between these, there's only this data. The number of intervals is totally dependent on the user. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Usually default 10 division is used, but you can change it to 5 or 100 maybe. So if you increase the number of intervals too much, then you can have some discrete intervals, because for example here the data number is 24. If you have larger or higher number of intervals, there will be some gaps between the intervals, because in some intervals there will be no data. It is better to use a smaller number of intervals than the data to be able to have a continuous histogram plot, let's say. Even for this, you can see, so between 648 to 652 we have 4 data. But for example, from 644 to 648, there is no data here. So there is a gap. Here also there is a gap. Oh, no, actually this gap is because we have 4 data and we just jump to the next. So there's only one gap here, you can see. Here from 652 to 656, we have 2 data. So these are the frequencies, how many data we have. And you can see upper and lower bound difference is the same for all intervals. And it goes up to 676 to 680, and it has only one data. Now we define the frequencies, lower and upper bounds. Now we can just have the intervals by using this data. These will be y values, and these will be the x values. And let's see how it works. You can see here, this one is from 636 to 644 actually, and we have an interval or bin, actually a shape of bin, and we have only one frequency, so it's straight at top, only one. Here as well, 642 644, we have only one data, so frequency is 1, but here there's a gap. It's because we don't have a data here between 644 and 648. So it continues like this. For example, between 648 and 642 we have 4 data. That's why this is up to 4. Then 3, 2, you can see. Then 3, then 5 here, then 3, then 3, then 1 and 1, up to 6.8. So you can see, especially in the middle, we have more frequencies of these histograms, and it's obvious that the mean will have more data, actually closer to the mean, and when we get away from the mean, we will have less data, so it's expected. That's why we have such a distribution, as you can see here, if we try to continuously plot a function like this. And this function is basically a bell-shaped function, symmetrical bell shape, and it's called normal distribution. And these bins shows the histogram. If you don't plot this, it's just histogram, but you can plot this as well, like this, by taking an average of each data. And this normal distribution with a symmetric bell shape basically means we have a normally distributed data from the mean, let's say. from to the right to the left, the distribution or the deviation is the same. So standard deviation can be think of the same, plus minus. And here, as the number of data points increases, the histogram could approach the smooth bell-shaped curve called the normal distribution, as you can see here. So standard deviation doesn't mean that the difference from mean is directly from here to up to the end. No, it is not like that. Standard deviation, actually, it just covers 68% of the data. So basically maybe up to here and up to here. So we have the mean here, 6.6. And from mean, standard deviation just gives a 68%, maybe 34% here with standard deviation plus, and 34% here minus sy. So this deviation, and if we add 2 sy and 2 sy, then 95%. So maybe up to here in that scenario. We have sy and sy added, 2 sy's up to here. 3 sy's maybe 99. So depending on the number of sy's, summing or subtracting from the mean, we will have a certain percentage coverage of the data. You can see here. When we have a distribution of a data, a continuous distribution called statistical distribution, such as the normal distribution we learned in the previous slide, then it may be important to generate some samples from that distribution, or falling in that distribution, let's say. And it is used or it is generated using Monte Carlo simulation. And this Monte Carlo simulation, or the Monte Carlo term, is a reference to Monaco's Monte Carlo casino. It is started to be used there as generating some data. And in the engineering area, it was first used by physicists working on nuclear weapons projects in the 1940s. So the basic idea of Monte Carlo simulation is that we have a statistical distribution and we want to just generate some samples from that. And this is only possible because of the computer's ability to implement tedious repetitive computations in an efficient manner. And now in MATLAB, we have some functions to be able to generate data. For instance, we have rand function, and m and n are the m by n matrix, or number of m rows and n columns, to generate some random samples from uniformly distributed data between 0 and 1. Uniform means we don't have a bell shape, but we have just a rectangular prism shape. So we will have a lower and upper bound of it, and we will be able to generate. So lower bound is 0 and upper bound is 1, and we will generate data between these using this function. And R is the number of samples. Actually, no, not number, the matrix of samples generated. If we want to have another interval, so a lower and upper bound, then we can generate data from here between 0 and 1, and we can multiply it by the difference of upper and lower, and sum with the lower. Then we will have the values in the magnitude between lower and upper bounds, as you can see here. Next, we can show how to generate data not from uniform but normal distribution, because it's generally encountered in the data statistical calculations. We use rand n. N means normal, and it is the same m by n matrix of random samples from standard normal distribution. Standard normal distribution means we have a mean of 0 and standard deviation of 1. So these are numbers. These are numbers are again between 0 and 1, but the standard deviation is 1 and mean is 0. Actually, it can be -1 to 1, we can say. Actually, standard deviation doesn't mean it will be up to 1. It can be 2 as well, because up to 1 is just this 68%. 1 to -1, actually. It's 34% of the data from one side. So, but we want to have these and run normally distributed data for a certain mean value and standard deviation different from these. Then we can use this standard normal distribution generation, have the numbers and multiply it by standard deviation and sum with the mean value, which is shown by mu here. And it generates random samples from normal distribution with a mean value of mu and standard deviation of st. There is another function, norm RND. It is the same as this one. It generates n by n matrix by using the mean and standard deviation of the samples from normal distribution with the same mean and standard deviation. So you can use either this and this interchangeably. There is another function, random, and it can generate samples from any distribution. It can be normal, uniform, or a different distribution like log normal, Weibull, exponential distribution, etc. Those will have some parameters. For normal, for instance, let me show the function. For normal distribution, we have two parameters, which is the mean and standard deviation for A and B. We don't write C and D here. Then we can generate data from the normal distribution using mu and SD. If we have another parameter, it can have up to 4 parameters actually. We can generate these random distributed samples from other distributions as well. You can check MATLAB help file or documentation file to see which distributions you can use for further investigation of this or further explanations of these. In this slide, we have the same example of the previous examples. You can see here same data, and we want to calculate the statistical parameters using MATLAB functions. Basically, in the previous example, we used only hand calculations. Now we want to use MATLAB to have these. So first in the MATLAB, we need to set the data as a matrix. You can see here in a column wise with semicolon. S is the data. So now we can use this in a short format to see like the significant figures in a short way. Mean S gives us the mean, median S and mod S, we didn't learn these, but these give other statistical parameters. And when you write these, the results are 6.6 is the mean that we calculated with hand calculations as well. These are the results of median and mod actually. Okay, the standard deviation and variance. Basically, variance is just var function, and it gives us the variance that we calculated from the hand calculation. It is the same. Standard deviation function is std in MATLAB, and when you write s, which is the data, it calculates the standard deviation for the data as the same as the one that we calculated from the hand calculations. So we can check the minimum and maximum of data. These can be important. Min s gives the minimum value, which is the first one. The max S gives the maximum value, which is the last one. If the data is not ordered, these will be important to find the minimum and maximums. And the range of data. The range basically is the difference between max and mean. So this can be important if we are especially dealing with uniform distribution. The range is 38.38. Okay, now we can generate histograms based on this data. And when you set this hist s is the data, hist is the function to generate histogram data, it gives us n, the number of elements in each bin, the frequencies actually. And by default, this creates a 10 interval histogram. But you can change the number of them. And x shows the midpoint of each bin. So there is lower and upper bounds, and there will be a midpoint. It shows the midpoint to plot these. This doesn't plot a figure, and also this hist function is not supported anymore by MATLAB. For the new MATLABs, I mean, it still works, but it's not recommended. You can use this histogram function. And by the way, when you use hist, n is, as you can see, the frequencies, and x's are the means for each of these 10 data. And in the new, as a new function, histogram as data, and 10 is the number of bins actually. 10 intervals or 10 bins we want. You can change it to 5 to 100 as well. If you don't use any initial definition of inputs, then this will plot the histogram automatically without showing you the values of n's or x's. If you want these, just put the bracketed, info here as well, equals histogram s10. Then you can get the n and x maybe, but this time it will not show the plot. To be able to have the plot, just use this function. You can see the histogram here with the frequencies. For example, the third one is 3, here it agrees. And these are 2, 2, 2, as you can see here, the frequencies. So this is the histogram of the data of this. We plotted this already in the previous slide from the book, and it is the same actually when we have 10 intervals. We can also generate a normal distribution for the data in MATLAB, and let's show that too because it can be relevant. So for the example 12.2, we calculated the mean as 6.6 and standard deviation as this value. And to use normal distribution and generate data from normal distribution, for example, we will generate 1,000 samples. And we calculated these from 24 samples actually, but from those 24 samples, we can assume a normal distribution and generate more samples, let's say 1,000 samples from the normal distribution. And if we want to generate it, basically we set the mean is 6.6, ST is this, then the number of data is 1,000, and you can use this function that we showed before, norm R&D, the mean standard deviation, and I want only 1,000 sample in a vector wise. So this is the number of rows and column number is 1. So it's a vertical vector with 1,000 samples. Now we can use these R's to plot a normal distribution. How can we do that? We can do that by using hist_fit. Hist_fit both shows a 10 interval histogram as well as it fits a normal distribution with a continuous bell shape. You can see on the right hand side, this is the 10 number of intervals. Of course, it defines the frequencies based on this 1,000 number. That's why the frequencies are very high. For example, 250 of them are in between 6.6 and 6.4. And it's expected because actually mean is 6.6 and it has to be symmetrical, and especially when we have very large samples, it is more clear to have a symmetrical bell shape normal distribution, even with the histograms actually. You can see here. And this red curve is plotted by this normal term by this hist_fit in MATLAB. You can also use this hist_fit for the initial data, 24 data. You need to just define here, instead of R, define the 24 data and write this again. It will show us both histogram and the distribution for the actual data as well.